Okay. You guys, the more enthusiasm, the better. Last class was dead. Also, half their class was gone. It was a little bit of a struggle. I could totally use some enthusiasm. So let's quickly take a stand up. Let's twirl around 2 times. Give somebody a high 10, and let's go. Because I need you guys to be on fire today because I am dragging. Let's go. Let's go. Up. Let's go. Poor Vico. You're like, Come on. High 10. Come on. Some of you guys are already sleepy. Wide awake?
Come on, Robbie, get up. Let's go.
Robbie, doing all right? All right. Here we go. Let's sit and let's go. Section 9.1. Did anybody show Robbie how many pages to skip for notes if he needs it? Are we good? All right, factorials. Factorials. Yesterday we got to this page, but barely. I did show you a factorial besides 0. 0 factorial is kind of weird, kind of lame. If I had a little more time, I'd try to prove to you why it is. If I could remember the proof, it's been a while. Factorials are a special type of product. 1 times 2 times 3 times 4, all the way up to n. Now some of you, if I were to ask you what 5 factorial is, you would have been 5 times 4 times 3 times 2 times 1. And you're not wrong. You're not wrong. However, we're redefining a factorial, or at least kind of changing the orientation in your mind, because when we get to expressions, variable expressions with factorials, it's going to be way harder to count backwards than it is to count forwards. Factorial is a special kind of product where you are multiplying by all the whole integers 1 through n, or 1 through whatever number is with the factorial. So 5 factorials, 1, 2, 3, 4, 5, all multiplied together. Anybody have that? Mental mathers? What's 1 times 2 times 3 times 4 times 5? 120? Good, 120. It's going to be a little bit helpful. A little bit helpful. Do you guys know how Mr. Che and Mrs. Leon totally have like square root of 2, square root of 3, square root of 5 memorized within so many decimal places? Huh? For factorials? Oh, for the square roots. Yeah. No, that's what I mean. There's a way of, or they have purposefully or even accidentally memorized some of those key square roots because they use those figures over and over. And there are different mnemonic ways of memorizing them. That's kind of how I am with factorials in the sense of, well, 1 factorial is easy. It's just 1. 2 factorial is easy because it's 2 times 1. It's 2. 3 factorial is 6 because it's just 3 times 2 times 1. 4 factorial is, well, 6 times 4 is 24. 5 factorial is 24 times 5, so 120. 6 factorial is going to be 720. 7 factorial. Now, I don't necessarily need to know them all, but it is something kind of random, kind of like the radicals are. Factorials come back in calculus BC. Not that all of you guys are necessarily going to get there, but it is going to be helpful for some of you at some point to kind of have these special numbers. Maybe not totally memorized, but at least so where you can recognize them. And so, the most basic factorials, what? 0 factorial is 1? Yeah, it is. 0 factorial, 1 factorial, 2 factorial, 3 factorial, 4 factorial, 5 factorial, 6 factorial. Every time you're just multiplying by the next number. So 2 factorial times 3, 3 factorial times 4, 5 times 4 factorial, 6 times 5 factorial. Every time you're just adding on 1, 2, 3, 4, 5, and 6. 1, 2, 3, 4, and 5. 1, 2, 3, and 4. You're just adding on another multiplication every time. So that's one way that counting up is helpful, because it's like, oh, 5 factorial is 4 factorial times 5. But another reason it's really helpful to count up is because when you get to an n, you don't really know where to stop. So if you had to count backwards, you would do n times n minus 1 times n minus 2 times n minus 3 times n minus 4 times n minus 5. I don't know when to stop. But if you go forwards, okay, it's 1, 2, 3 all the way up to n. Who would be right before the n? Well, these are always 1 apart. So if n was 10, that would be 9. If n is 100, that'd be 99. It's n minus 1, n minus 2, n minus 3. So this one, these two, are actually super different. Because this one is, according to PEMDAS, 2 times n factorial, which would be 2 times 1 times 2 times 3 times all the way up to n. But what's this one? What's the one down below? It's not 2 times 1 through n. Yeah, it's 1 times 2 times 3 all the way up to 2n. How is that different? If this was 2 times 10 factorial, it'd be 2 times 1 through 10. If this was 2 times 10 factorial, it'd be 1 through 20. Does that make sense? So it's very different, 1 through 10 times 2 or 1 through 20. Which one's stronger, do you think? That one or that one? 2 times 1 through 10 or 1 through 20? Ooh. Ooh. I didn't know I'd trick so many of you. If n was 10, wouldn't this be 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8 times 9 times 10 times 2? What's this one? Does this distribute? No, it's just multiplication. So get that big old number times 2. What's this one? Who's bigger? That just has a 2. That is 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Way bigger. True? Okay. Just double checking. Choop, choop. So what if, why am I having you cover factorials? Because with sequences in series, especially in BC, factorials kind of start showing up. In nth term formulas? Yep, in nth term formulas. In nth term formulas. All right, the first 5 terms. Oh, remind me from yesterday. First 5 terms. What's the notation for those 5 terms? Good. The notation is, first term is A1. Oh, wait. Awkward. They changed it on me. Normally, Gavin was totally right. A sub 1 is the first term. But remember in our notes we said n can start at 0 or 1? Kind of has to do with physics. If you say at the beginning in a physics problem with time, x being t, time is 0. Yeah. Okay. True, but we have to make sure that we are in line with what the problem is giving us. Does that make sense? Because if we were to start at 0 just because we want to start somewhere lower, but really they want to start at 1, we'd be in trouble. So watch out. But this one does start at 0. So we're going to do, which in some senses, Kyle's like, hey, it's going to be less work because 4 factorial plugging in is a lot lower than 5 factorial. That's true, but it's also kind of trickier in our brains because if I say the 5th term, isn't the 5th term a sub 4 now? Oh, that's awkward. The first term is a sub 0. The second term is a sub 1. Oh, okay. If we start at 0, it's just going to feel a little weird in our heads, in our minds, because we're going to say, oh, the third term is a sub 2. But it's still right. It's still right. So if we start at 0, plugging in, 2 to the 0 over 0 factorial, then 2 to the 1 over 1 factorial, then 2 to the 2 over 2 factorial, 2 to the 3 over 3 factorial, 2 to the 4 over 4 factorial. What do we got? Careful. I know it looks like 0 in so many ways, but what's anything to the 0 power? And that one's defined to be weird, right? Okay, but then go for it, Robbie. Then you saw 2, because it'd just be 2 over 1. And then it'd be 4 over 2. Oh, that's a weird, look, 1, 2, 2. Huh. Then 3, 2, 1. 1 and 2 sixths, or 1 and a third, or 4 thirds. I just reduced. 2 to the 4th. Wait. Okay, hold on. You don't have to start over again. Isn't 2 cubed 8? So times another 2 is 16. And then isn't 3 factorial 6? All we have to do is times 4, so 24. See what we're doing? What's another way of doing it? I'm going to get there. I'm going to reduce it, and some of you already are. I don't know if it's easier in some of your brains, but you could have also, I know, not written it out, but thought about it. Couldn't 1, 2 go away and another 2? Oh, huh, isn't it just 2/3? Ooh. It's kind of fun. Now, did some of you finally figure out that 8 goes into 16 twice and 8 goes into 24 3 times? Yes, but isn't the math technically simpler to go that direction? Just an idea, just a thought. Just an idea, just a thought. Oh wait, that wasn't our final answer though. Wasn't our final answer just the first 5 terms? Okay, so 2/3. Our final answer would be sequences separated by commas. 1, 2, 2, 4/3, 2/3. Huh. This is a weird sequence, isn't it? If I was to ask you for the pattern, would this have been obvious to see? 1 goes up to 2, stays at 2, goes down to 4/3, goes down to 2/3. I don't know what's going on. It's a weird one, right? But is there a formula that's behind it? Yeah, there is. Ooh. Ooh. You know what I just showed you a second ago? How sometimes it's easier to break down things? Could we do 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8? Whew, huge number. All over 1 times 2 times 3 times 4 times 5? Yes. But what else could we do? Map them out. We could map them out. There's a little bit faster way, but that's okay. What ends up going away? Something didn't go right. Anyway. What's another way of getting there? Couldn't I have also thought about this as 5 factorial and 5 factorial times 6 times 7 times 8? Right? Any factorial can be broken down into a product of lower factorials. Now I can't do 5 factorial, 3 factorial, because 3, 2, 1 is not 6, 7, 8. But I could say, hey, 1 through 5 and a few more, and those go away. Either way, those go away, and I end up with 42 times 8, which granted isn't like the most fun thing in the world to do, but it's also not horribly bad. What? 336, yeah? Okay. But how do I use this idea with numbers to help me with, I'm telling you that this can reduce, but it's weird because there are n's. Who's the bigger one? N minus 2 factorial or n factorial? Who has more terms? Yes. But, okay, well wait. The bigger one for factorials held in the smaller one, right? Like a part of 8's factorial was 5 factorial. So if n factorial is the bigger one, doesn't he hold within him n minus 2 factorial? So this guy's going to be 1 times 2 times 3 times 1, all the way up to n minus 1. Nope, n minus 2. What would be the next term after n minus 2? Don't we always just add 1? Add 1, add 1. So add 1. What would be after n minus 2? N minus 1. What would be after n minus 1? There he is. So couldn't all of that go away with all of this? Or couldn't we also say that n minus 2 factorial is down here also, but then you also have an n minus 1 and an n? Which means 1 over. Well, that's a lot easier than that. That's a lot easier than that, Kathleen. I started by asking which one's stronger. And since this numeric value will always be lower, because factorials can only use positive numbers, not negative. Since this will always be lower, whoever's the bigger number is the stronger factorial or includes more terms or more values. So once some people answered n factorial is greater, and I agreed. then I said, okay, well then the greater factorial will always hold within it or be comprised of the lower factorial and a little bit more. So I started with the lower factorial and said, okay, he has everybody 1 through n minus 2, and n has 1 through n, but I actually said something to the effect of he has 1 through n minus 2, like this guy, he holds in the lower factorial. And then I said, what would come after that? You add 1 to n minus 2 plus 1, like you always add 1 to get to the next guy. 5 plus 1, 6 plus 1, 7 plus 1. n minus 2 plus 1 is n minus 1. n minus 1 plus 1 is n. Then I was able to go ahead and reduce the common factors, and I was left with. Does that make sense? What's hard is that if you guys are so used to 8 factorial is 8 times 7 times 6 times 5, as soon as you get to n factorial, you're like n times something before times something before. But if we write out expressions for that something before, n times n minus 1 times n minus 2, and if we started somewhere like 1, 2, 3, then I can actually do some of this reducing that would be kind of impossible if we only counted backwards. We wouldn't really know what's going on. So counting forwards with factorials, once again, is pretty important as far as having a good understanding of a factorial that will also apply to n's or to variables. If you guys want, if this is a tricky idea, you could come back here and you could, just to remind yourselves, you could put an n minus 2, you could put an n minus 3, just to remind you of how you get earlier or prior terms in a factorial and how you get later terms. You could actually do another one and do n plus 1, n plus 2, etc. if you wanted to keep on going even further. But I guess that might convolute things just a little bit. So maybe it'd be nicer if you did like another one, like n plus 1 factorial would be 1 times 2 times 3 times 4 times n minus 1 times n. We can just count 2n adding ones or subtracting ones. I don't know if that helps, but all right, factorials. But there's one more big idea in section 9.1, sigma notation. Sigma notation. Hey, this shows up on SAT stuff, doesn't it? Especially the math subject 2. Subject 2 math, however you say that. The SAT subject test for math. Series. If you guys looked at chapter 9's title, sequences, comma, series, comma, probability. Remember, section 9.1 is a big old Mama Bahama intro. Intro. Section 9.1 is a big old intro section. And so it's introducing also us to sigma or summation notation. Yeah. Yeah, but I think just one line is good, Gavin. I think just one line is good. You guys remember back from when we were talking about Greek letters with angles and stuff, right? This is the Greek letter sigma. It's a capital sigma. First of all, just starting off with, I'll zoom in and I'll scroll down. Series versus sequences. Series say, hey, take a sequence A1, A2, A3, A4, and make it an, or a sum. I was going to say an infinite sum, but sorry, this is finite. Make a sum. So instead of A1, A2, A3, A4, it's A1 plus A2 plus A3 plus A4. Sigma notation says, oh, well, that's tedious to write like a pattern or a sequence of terms that have a pattern over and over and over again. If I have to add up 10 or add up 20 or add up 50, it'd be so much nicer if there was a shortcut notation, that would allow me to summarize a big old sum, however big it is, into a nice little shortcut, in a sense, program. And so remember, if you guys have seen these before, you saw them in Algebra 2, didn't you? Okay. When you saw these in Algebra 2, sorry, our curriculum changed a few years ago, and I'm still trying to figure out exactly what's in Algebra 2. That we plug in I equals 1 is our lower bound. Doesn't always have to be 1. Sometimes it starts at 0. It can technically start at 2 or 3 or 4 if they really want it to. But that's our lower bound. That's the first value that we plug in, if you guys notice over here. A sub I, who's I? This guy. Oh, A sub who? Start at 1. Okay. And then we count by whole numbers, just because these are 1 through n are indicators of the nth terms, indicators of what place we are if you're starting at 1 in the series. I equals 1 is the lower bound, n is the upper bound. Lower bound is where you start, upper bound is where you stop, and you are plugging them in, yeah? Lower bound is where you start, upper bound is where you stop, and you're plugging them in. You're going by whole number integers, as we've been talking about, sequences and series. N is always positive integers, positive counting numbers, no rational numbers, no fractions or decimals. Positive integers. And so properties of sums down below, just a few things that are true with sigmas. As you guys are getting these down, make sure your calculators are out if you have not yet gotten them out. I've been asking you guys to bring your calculators. If you haven't been, you might want to start. It doesn't show up very often in homework, but there is a graphing calculator section where they want you to do something, and there is a new mode that I want you guys to go in. So once you have this written down, go find the sequence mode. Mode, there's a button, right? Actually, not sequential. Sequential and simultaneous. Sequential and simultaneous is talking about Y1s, Y2s, Y3s. Whether they should graph, or it should graph, your calculator, Y1 first, then Y2, then Y3, to graph in sequence, one after the other, or whether you want Y1, Y2, Y3 graphed all at the same time, simultaneous. Yeah? So sequential and simultaneous is saying, do you want them graphed sequentially, one after the other, or do you want them graphed simultaneously? That has to do with graphing. Don't touch that one. Instead, mode. Most of you guys should be in FUNC, function mode. Function, par, parametric, pole, polar. The last one, SEQ. There you go, sequence mode. Func, par, pole, SEQ, sequence mode. Once you guys go into sequence mode, I want you to go to your Y equals and see what's different. We're going to talk about this before the end of class and talk about in homework where it shows up, because there's a section, I think Adam and I were looking at it yesterday. SEQ mode. Try to hit the variable button. Try to hit an X once you go to Y equals. Ooh, what letter is it? It's an N. N. Haven't we been talking about N's quite a bit, guys? We'll get back to our calculators in just 1 second. These operations, no, properties, sorry. My words that are coming out of my mouth today are a bit jumbled. I apologize. Properties of sums. Hey guys, if you see a sigma with a C, like a sigma with a 2 or a sigma with a 10 or a sigma with a 30, why does it equal C times N? Well, it does because if you were to write it out, is there an I place to plug in? Gab in this way. Is there an I place to plug in? Nope. So that means, okay, for the first term, I don't know, it's C. For the second term, I don't know, it's C. For the third term, I don't know, it's C. For the fourth term, how many C's are you going to have? I don't know, however many N's. Or however big N is. If you're going from 1 to 10, you're just writing C 10 times. If you're going from 1 to 20, you're just writing C 20 times. So if it's just sigma of a constant, you're just adding C, N times. So C times N is a nice shortcut way of doing that. If you, instead, have C times A sub I, wouldn't that be C times A1 plus C times A2 plus C times A3 plus, well, all the way up to C times A sub N? If this is a sum, what can I do to the constants? What can I do to anything that's shared? Factor it out. So I can pull it in front and say, okay, it's A1 plus A2 plus A3 plus A4 times C. See? Never mind. Number 3. If I had sigma of AI plus BI, wouldn't that be A1 plus B1 plus A2 plus B2 plus A3 plus B3 plus all the way up to AN plus BN? But what can I do with sums? Rearrange to get all the A's plus all the B's. So the associative property also works with sigmas, which is kind of cool because it'd be A1 plus A2 plus B1 plus B2. Anyway, that makes sense. And then subtraction is very similar. So properties of sums, I think the trickiest out of all of these is probably this one. That one's probably the trickiest because all the rest are like, okay, plug in 1, plug in 2, plug in 3, plug in 4, and it should make sense, but that first one is a little bit weird, so I wanted to make a special note of that. So, how can we expand and solve the following? Don't go to your calculators. I know they're there and they're just calling for you to use them. I know there is an operation in there and everything, but just to get the idea, how would you expand? Ooh, expand, condense. This is a thing with logarithms. This is a thing with series. Exponentials, a little bit. Exponential notation, I guess, a little bit. Okay, what would you guys do in letter A? You have options. All right, so 3 times what? 1 plus 3 times what? How long do I keep going for? Oh, stink. 3 plus 6 plus 9 plus 12 plus 15. This is so hard. Why didn't you just pull out the 3?
Whoa.
Isn't this just 3, 6, 10, 15 times 3 is, I can't write, but I can multiply. Do you see why I say you can pull constants out? The 3 could have come out from everybody, and you're like, oh, there's 1, 3, 2, 3s, 3, 3s, 4, 3s, 5, 3s, so 1 plus 2 plus 3 plus 4 plus 5 times 3. All right. Where's the sigma in your calculator? It's not the y equals. We're coming back to that. Where's the sigma in your calculator? Who's found it? Aiden, where is it? No, he did that little shortcut menu. You know how you guys get fractions? The alpha y equals? It's alpha, is it the second one, Aiden? Good, alpha window. Alpha window, there's a little shortcut sigma. That's kind of nice, shortcut sigmas. But where's the normal place? Math, all the way down to summation. Now, sadly, for this test, any of you guys with the yellow button, you might want to borrow my calculator. Look on with someone in your groups, because the old calculator with the yellow button does not have a sigma. It's super sad. Totally not impossible to do, and yet it's way too... Yeah, try to fill in and get 45. Check it out, help your groups. Check it out, help your groups. Does everybody know what they're doing? If they don't have the right calculator, you're showing them so that they can do it unlike my calculator. Kathleen, we can talk about the end of whatever's going on. It's probably about your schedule and stuff. Letter B. Letter B. What do you do? Okay, stop. How do you actually plug it in, though? 1 plus 9 plus 1 plus 16 plus... Wait a minute. Why am I starting at 3 squared, then 4 squared, then 5 squared, then 6... 6 squared is not 26. It's 36. Because can your lower and upper bounds change? Yes. And so if they say start at 3, I start at 3. If they put a k, I say, okay, whatever, k. K. Anyway, never mind. But in your calculators, how did you guys put in the letters for your sigma? Did you go find a lowercase I? Where's the lowercase I? That's awkward. Do you have to use I? Or could you, in your calculators, just be super snazzy, and could you just use like N? Use your variable button if you're in sequence mode. Or use X if you're in function mode. All you need is some sort of variable if you're in your calculator. All you need is some sort of variable if you're in your calculator. But according to our properties, we also could have, well, I don't know, this would have been a bit more awkward, but we could have split this up to be k equals 3 to 6 of 1 plus 3 to 6 of k squared, which we would say 1 times n, but it's not 1 times 6, sadly, because it's 3, 4, 5, 6. There's only 4 ones, 1 plus 1 plus 1 plus 1. So that's a little bit awkward once the bounds change from our properties on the page before. But then we would have like our 9 plus 16 plus 25 plus 36. Have you guys already found this one? What does it end up being? 20, 45. Yep. Okay, so sigmas. What are we left with? There are infinite series? Hold on, pause. I have you guys in your calculator in sequence mode. I want to look at something in homework before it gets to series, infinite series, what we're looking at right now. I think there's something that says something about your graphing calculator. Ooh, do you see it? 27 to 32. In your calculators, which sadly, sorry, my brain's been on overload. Mrs. Christensen still needs to get me the new license so I can turn back on my graphing calculator. Hey, who has a graphing calculator with a light-up screen? Can I borrow it real quick? Awesome, awesome. Because I have a webcam. Go team. All right. Oh, that doesn't work. Okay. Ha. Ta-da. Okay. If you guys are looking at, say, graphing calculator, and you are in sequence mode, right down here, function needs to go to sequence. Any calculator should be able to do this. It should be able to go to SEQ mode. And then if your y equals, oh, Kyle, your poor little calculator is sad and battery is dying. Let's say I was to want to graph a sub n equals 2/3 times n, so number 27. And I want to graph the first 10 terms. We're going to go ahead and start at, look, n begins with 1, so n equals 1. My u of n is like my a sub n. It's just the formula in terms of n. So I could just put my alpha y equals, I could do my 2/3 times n, hit that little variable button right here. Now, it does ask me if I try to go graph right now. Oh, it does graph. Well, that's nice. Didn't used to. Some of your calculators might require you to put in a u of 1 and u of 2. It says u of 1 and u of 2 because Fibonacci starts with 2 different numbers. Other sequences only start with 1. So you could go ahead and start it and say, if I plug in 1, I get 2/3. That's my first term. If I plug in 2, I get 4/3. But if you guys notice, that doesn't really change much. Why are there just separate dots, and why aren't they connected? It's not a line because n doesn't equal all the decimals in between. N only equals 0, 1, 2, 3, 4. Actually, it doesn't equal 0 because it started at 1. What if we were to try to plug in something else with a fraction or a decimal? Do sequences work with fractions or decimals? 0.5. No, because n can only be what kinds of values? Numbers, like 1 or 2 or 3, and so you're going to have these little dot graphs. But if you notice in your homework, don't you already see that sequences are only dot graphs anyway? So if they're asking you to graph the first 10 terms, I guess you could go by hand, plug in 1 and 2 and 3 and 4 and 5, or you could just go ahead and once again, go to mode, go to sequence mode, go to your y equals, type in your function, and it looks like at least some calculators don't even need you to put in your first couple terms if you have the n in there, because they'll just go ahead and give you exactly what you need. There you go. Was there any other place you needed to use your calculator in homework? Oh, here's one. But didn't we just talk about how to find the sum in your calculator using a graphing utility? Now, some of homework is going to have you come from a pattern backwards to a sigma, trying to write that in. But what we're talking about here at the very end of class is, kiddos, check out numbers 89 to 92. Ooh, what does it say? Partial sum? Partial sum? I don't get it. In our notes, it says infinite series. In our notes, it says infinite series. What is an infinite series? An infinite series says plug in plus dot, 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 keep going. An infinite series says and dot, 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 keep going. Now, we're not going to spend tons of time on this. There's actually 2 pages. Oh, just 1 page. When it says third partial sum, I want you guys to think, because you're going to see that wording in homework. Find the sum of the first 3 terms. If it says third partial sum, partial means it's not the whole thing. Find the sum of the first 3 terms. And this one starts at 1, so it's going to be 3/10 plus 3 10 squared is 100ths, plus 3 10 cubed is 1,000th. And I'm going to stop there. I'm not going to go to infinity. Wait a minute. Isn't that 0.333? Oh, what would be the infinite sum? No. If you add and add and add and add and add, it's going to get bigger and bigger and bigger and bigger and bigger. Or is it? Isn't this just going to be 0.33333333? Which is infinitely adding can equal a constant? Bye, guys. Later. Toodles.